So with this question, the first thing we should do is draw it out, okay? So we've got the upper arm, we've got the weight at the end, we've got the center of mass, and we've got the bicep lifting upwards, okay? Not in a perfect straight up, it's lifting in 86 degrees. Boy, howdy, that is just ugly, okay? So then that is going to be 2.5. This right here is going to be 12.5. And then this right here, these are both pulling downwards because that's the weight of the arm. Is going to be 25. Okay, so that's our distances. Now the loads are going to be 20 kilograms and then the weight of the arm is going to be 5 kilograms, which that is one heavy forearm. Okay, so the formula that we're going to end up making is going to be the bicep force times 2.5 equals, okay, open parentheses, 5 kilograms times 9.81, because that's gravity, times the distance, which is going to be 12.5, close parentheses, plus 20 kg times 9.81 times 25. Okay, so that's our first part of the formula. But then, since we're pulling in a slightly backwards angle, okay, we then have to do, because we're solving just for the vertical component right now. We're not solving for the actual hypotenuse, which is what we need. So if we know that this is an 86-degree angle, which of our trig functions are we going to use? Which we're going to use, guys? 3 options. What do you guys think it's going to be? Anybody? That's okay. So we have the biceps force that we just solved for is the vertical, okay? What we don't have is the hypotenuse, which is what we really need. So see, John, the adjacent, that's actually going to be the force pulling into the joint. The opposite is the vertical. And we don't know the adjacent. Nope. It's not cosine. It's going to be the sine of the angle. So, exactly. So what we're going to get is we're going to have a final formula of sine of 86 equals that actual the force we solved for before divided by the hypotenuse. So we're going to factor that. So we're going to get that force, okay, divided by the sine of 86 equals the total force the bicep is producing. And there's your solution. Ta-da! So what question would you guys like to work through next? Yeah, no worries. So remember, guys, with our good old SOHCAHTOA, we have to think back over here, okay? Where effectively what we're going to have is we have our angle. The hypotenuse is the combination of both your opposite and your adjacent. Now, since we know the bicep angle in this one, the adjacent is actually going to be the forearm itself. So that's actually the force that's keeping the bicep itself in the joint, because as you're lifting, you're slightly pulling the bicep literally back into the elbow, which is good because you're not going to dislocate yourself as you're doing it. Now, you then have the opposite, which is the actual vertical lifting force in this example. So we're trying to solve for the total amount of force we'd have to produce, which happens to be that hypotenuse. No worries, Haley. What other questions would you guys like to work through? Have you guys had a chance to look at the review? Actually, Braden, you're going to divide the total of those other forces by 2.5. Because remember, we still have force times force arm equals resistance times resistance arm. You have to make sure you stay balanced. Total amount of strain that an object experiences if it compresses 20% and requires 500 newtons of force to compress 5%, and it compresses with linear organization. Okay, so that means as we go from its initial length and we compress it, to go from its initial length to 5% shorter, we have to use 500 newtons, and it's linear. So that means it's going to keep going up in a straight line. So it takes 500 newtons for 5%. How many newtons do you think it's going to take for 10%, guys? Bingo. So then, John, what do you think it's going to take for 20%? Exactly. Boom. Good work. Now, that's linear. Exponential is going to be where it doubles and keeps doubling as it goes. So you go from 5 to 1,000 at 10, then you go from 1,000 to 2,000 at 15, and then you go from 2,000 to 4,000 at 20, because it's just exponentially climbing. Hey, appreciate you asking me questions. Yeah, no worries. So when we're talking about the facet joints, remember we're talking about the angle that the facet's in. So in the cervical spine, it's going to be more steep. It's going to be more directly stacked up as we get into the lumbar spine. So as that angle increases, we're actually able to deal with greater and greater amount of force. Yeah, no worries. So rotational acceleration is the same way that we're going to calculate acceleration in general, okay? Now, which way do you want to go at it from, Braden? Do you want to just say that we start at this velocity, we finish at this velocity? Or do you have something more complicated in mind? Okay, you don't need a radius or a mass if you're just doing rotational acceleration. All rotational acceleration is going to be is simply you've got an object that's going to be, oh God, that's just bad, rotating at a certain velocity. So if we say we start here and we're rotating at a relatively small velocity, and then we're going to increase it. So effectively, if we start off rotating at 10 degrees per second and increase to 100 degrees per second, and we do that in 1 second, we get a formula of effectively 100 degrees per second minus 10 degrees per second divided by 1 second, which gives us an acceleration of 90 degrees per second squared. That's it. You don't need a radius or mass. I just put that in there to confuse you guys. Okay, so Cass has got a good question of how does the inertia of a limb change if the weight is 10 kilograms and the radius of gyration goes from 1 meter to 0.5? So remember, we come back on over, we can see that our moment of inertia equals our mass times our radius squared. Okay? So that means we have, oh God, I am not good at straight lines. We went from being at 1 meter to now at 0.5. Okay? And the total mass is 10 kilograms. So that means we literally went from a inertia equals our mass, which is 10 kg, times 1 squared. Because remember, guys, now we're at our inertia equals 10 kilograms times 0.5 to the second power final. So we literally have gone from an inertia of 10 to an inertia of 2.5. Which means we're at 1/4 of our initial inertia. Yeah, guys, when in doubt, draw it out. You just got to draw it, and then remember, think about your units. What are the units that you're looking for? What are the units that you need to solve for? What are the units that you have to start off with? You're always going to have everything you need. Sometimes you're going to have more than you need. And that's when you need to think about, okay, I only need to be able to give this information. So if I only need to be able to give this information, I don't need to go through and use all this extra stuff. I just need to focus on what's necessary. Any other questions you guys would like me to go ahead and go through? Awesome. Okay, so Luke, if you're really trying to figure out the best way to go about it, as far as, what muscles are being used during different motions, it sounds odd, but go lift weights, go train those movements. So the next day you're like, oh my God, all these things are sore on the front of my neck, and then name them, because trust me, you'll feel them. And if you feel them and you've trained them, it's going to be a lot easier to remember them. So hence my advice for all this when it comes to the arms and legs and the torso, train the muscles. Now, also think about feeling those muscles contract when you're moving in those different planes so you can feel them actually working and doing their job. Yes, now be careful, guys. If you have not done any neck work and then you try to do a bunch of neck work, you're going to be really freaking sore, really sore. Like, I'm not kidding, it's bad. But that's why most bodybuilders have a better understanding of what muscles do what exercises, simply because they've trained them. They know those actions and they know the soreness they get the next day from doing those exercises. Okay, so let's go ahead and talk about a strain example. Oh, sorry. So effectively, we just talked through one of them. So, okay, so let's say we've got a linear, and then we have an exponential. Okay, so the previous example, when we were 5%, with linear, it was 500, and with exponential, it would also be starting at 500. Now, at 10%, we're going to be at 1,000, because linear is just that straight line. Now, exponential, and we're expecting exponential growth, which means we're going to be doubling. So we're assuming that it's doubling every effective 5%. So then we're at 1,000. Sorry. Also, now when we get to 15, that's where things are going to get weird. Because at 15, we're going to only be at 1,500, whereas with our exponential, we're going to be at 2,000. Then we're going to be at 2,000, and we're going to double again, so we're going to be at 4,000. So if we went up to 25, we'd be at 25. Meanwhile, we'd be at 8,000. Wow, that really screwed that up really quickly. But you catch my drift. Now, for Cass's question, how fast would you have to jump off the ground in order to jump off at least 2 meters in the air? Well, this is our old school kinetic energy equals potential energy, which means 1/2 of our mass times velocity squared equals our mass times gravity times height. Okay, so, well, since we have mass on both sides, they cancel. So we have 1/2 of the velocity squared equals 9.81, because that's gravity, times 2 meters, because that's how high we want to go in the air. So then we multiply each side by 2, so we can get rid of the 1/2. So now we have velocity squared equals 9.81 times 2 times 2. And then we can go ahead and take the square root of both sides. So that's going to give us velocity equals the square root of the combination of 9.81 times 4. Like I said, guys, you have all the tools you need. All the tools you need. You just have to think through, what can I use to solve for the information that I'm trying to solve for? What other questions you guys have? Okay, how do you find out the force produced to maintain arm positions when not parallel to the ground? All right. So let's say you're standing up and your arm is over here. Oh, dear God. So we have our angle. Now remember, we're going to take our center of mass of each of these, and instead of it being the length along here, we're actually taking the shortest distance between each. So effectively what you need to do is treat this like a triangle, and you just need to find the length of each of those arms. Okay. So Haley, in this example, if we know this angle at the top, all of these are going to be the opposite. So if we take the length it has from the center, we're going to constantly be effectively running the same formula of the sine of the angle equals the actual distance that we're trying to solve for of the lever to the actual like arm length distance. So hence when my arm's down in a lower angle, it's only here and over, whereas it's here, that's the actual, and we don't have to do any of that trigonometry. Now, with the shearing forces of the vertebrae, okay, if we've got our vertebrae over, because we're bent over, we have two force vectors, or we have one force vector always, which is just straight down, which means that we have a certain amount that's compressing and a certain amount that's shearing, like it's trying to slip forward. Okay? So if you're standing upright, thankfully your back doesn't look like this, guys. It's going to be a lot prettier. All of the force is vertical, which means it's all compression. Now, if we're completely perfectly bent over, then we effectively have no compression. It's all shearing force trying to slide you forward. Does that make sense, Luke? That's why those force vectors are so important. As I'll say it once and I'll say it again and again, when in doubt, draw it out. Yeah, no worries. Okay, so now remember, when it comes to energy, we've got a lot of different types, okay? So we've got kinetic energy, potential energy, and strain energy. The key is, Braden, some objects only have one. Some objects have every single one of these. So for total energy, you need to figure out which of them apply. So if you are running along the ground, you simply have kinetic energy. If you are jumping off of a high dive, you have, like literally just jump and let yourself fall straight down. You have potential energy. But if you run and then jump, you have both kinetic energy going forward and potential energy driving you downwards. So you actually add those two together, and that's how much energy you have. No worries. What else would you guys like to go and talk about? Okay, well, I'm waiting for folks to go ahead and maybe give me another question they'd like to review, and keep going through the wonderful, review paper or study guide. Guys, you make sure you go through it, make sure you understand it, put in the formulas. We can work through all these. How are you guys doing on your projects, and have you guys had a chance to do your video yet? So if you guys don't mind, put up in the chat which groups have actually done their video. That's okay. Okay, so guys, effectively, you guys are going to be solving for the same things we're doing here. Now, we'll take the soccer one because I'll probably be able to draw this out without making it too awful, okay? You're going to start off with your legs underneath you. Then, during the windup, you're going to pull that leg backwards. And yes, I know you have a knee and it'll be bent somewhere in there. Then you're going to go ahead and kick that leg forward so you can actually obviously kick the soccer ball for the force producing. Then after you kick the soccer ball, the leg itself is going to follow through. So you're going to have, if we're just looking at the hip, in the windup, you're going to have a negative velocity and acceleration because you go from here to here. Then you're going to have a positive acceleration and a positive velocity as you go and you kick the ball. Now, once you kick the ball, your leg is going to deaccelerate, but you're still going to have a positive velocity. Does that make sense? So force producing follow through. And from there, you can go ahead and have, whatever recovery they're doing. So you're going to be looking at those angles and those accelerations. So all you have to do for that is try to get, and that's why we did the goniometry lab, if you figure out effectively how many degrees did you move during each phase, then ask yourself how long in seconds was that phase. And if you know those two, you can derive the angular velocity and the angular acceleration. Now, once you have the angular velocity and angular acceleration, remember back to our formulas, you now can figure out the torque because torque is going to equal the inertia, which you are going to be able to solve because I've given you those formulas of figuring out what the mass and the radius of each of those limbs should be relative to someone's height. And you solve for the acceleration. So now you have the torque. And then if you want to figure out the force, well, remember, torque simply equals the force multiplied by the distance. So you're just looking at how far does that muscle actually attach from the joint that it's pulling along, and boom, done. That's literally how you're going to solve the math for each of your joints. So that's why you have to video it, and then you just play it back super slow and just do your best to time each of those phases so you've got the time and you're going to have your best guesstimate of how far you went within each of those time periods. Any other questions? Anything you guys want to work on, review on, otherwise? Okay, cool. Effort arm is 20% closer. Then the point of insertion. Okay. Oh. So effort, and then les résistances. Haley, go to the YouTube site. There's examples of it. You just got to look at the data there and copy it over for the labs. You only turn in the joint that you did for your paper. That's it. And all of you guys are going to put in all of your information for the presentation, which is just going to be a PowerPoint that you guys are going to put together, record your voiceover, and then you guys are going to submit that, just one per group. But you need to solve for your joint. This is why it's great, because you guys are working together. But if someone in your group doesn't do the work, it makes you look better because you'll have your full breakdown of the shoulder, which will be a good slide, and you'll have the voiceover and everything set up, like the GIFs of the exercises being performed. And then the other group will go, or your other person in your group will go and be like, the elbow moves. Be like, wow, that was bad, which makes you look better by comparison. So if someone in your group is slacking, it's okay to put me on the emails like, hey guys, this is due. I'm submitting the paper, or submitting the presentation. If you don't have it to me by this time, it's just getting submitted, because it'll be really easy, because you just make sure, like, here's where their slide should have been. It'd be like, perfect, they get a 0. You guys did better. But back to Luke's. So it says it's actually 20% closer. And that's because of those angles and when we're going to find ourselves to be actually perpendicular. Okay. So we've got 10 kgs over here pulling us down at a distance of 0.45. And we're lifting up over here at 0.12 meters. But that's actually going to be 20% closer. So what this means is we have our actual effort is going to be multiplied by, and then we put in parentheses, 0.12, which was going to be times then 0.8, because it's 20% closer, which means it's only 80% of its initial distance, then equals 10 times 9.81 times 0.45. All right, Luke. So just having a little fun with math. Okay, so now angular inertia. Remember, the inertia equals our mass times our radius squared. So literally, just equals 100 times 3 to the second power. Done, that's it. That's okay, it's okay. Guys, once again, I'm always gonna give you what you need. You just need to think through, how do we apply this information? What are we trying to solve for? What are the units? What do they mean? That's why even before we moved to this online, every time there was an exam, every student, I would literally have this projecting on the screen the entire time, and then handout sheets for the students that had to go take it over in the computer lab. Because I have no interest in your ability to memorize formulas, because let's face it, when you become professionals and adults, you guys are going to, sorry, professionals, you guys are already adults. You guys are going to just look something up if you need to remember how to run the formulas or what they mean. It's the application. It's understanding how to think your way through it and try to figure out, okay, what is this showing me? Why do I care about this? That's the big key. So, are there any other questions you guys want to review now? And if you guys don't have any other things you guys want to review now, that's okay. We can let you guys out early today if that's all right with you guys. But here's the thing. Whenever we meet on Tuesday, I'm expecting there to be a lot of questions that you guys want to review on. If there's no questions, your exam will be due on Thursday because there weren't any questions that you guys wanted to review on. How does that sound to you guys? Yes or no? So either we're going to review more on Tuesday, or we're just going to make the exam be on Tuesday. So if you want another review day, please say yes. If you would prefer to take the exam, please say no. And because I believe in forcing everyone to vote, by choosing not to vote, you are in effect saying that you would like to take the exam. So make sure you guys are clicking that in the participants where you're going to see the poll where you can click yes. Okay. All right. Now, guys, you should be slightly concerned because 4 of your classmates have not voted, which means they would prefer to take the exam on Monday, but you guys do carry it because you have the majority. So stay safe. Have yourselves a great rest of your week. Please, please, please come with questions, and they can be straight from the review. Okay? Try to work your way through them. try to figure out at what point are you not able to solve it anymore, and then come ready to obviously paste that into the chat, or you can unmute yourself and be like, hey, can we review question number blank? So stay safe, guys, and I will chat with you guys more soon, okay? Enjoy the rest of your day. Sounds great, Luke. Have a great day, guys. Bye-bye.